Oh, you're doing full virtual cam this time. Fancy. Okay. I'll pick that up.
The 10th, so I got to get used to being on or like being in public on cam or whatever. So figured I would do this one on cam as well.
Nice.
Cool. All right, we are tracking and good and live and good to go whenever you are, man.
All right, cool. Well, you said you're good, Gio?
Almost here. Yeah, just like 10 seconds. It's starting now.
All right, cool.
It's going to be, yep. Good to go. Cheers.
All right, cool. All right, so this is How Math Became Reality, a comprehensive look at the history and classical experimental evidence that's put forward in support of relativity theory. So for the abstract, we have special relativity and general relativity defined. A quick summary of special relativity is that it's a theory to derive to explain motion and acceleration, and it proposes reference frames as a mathematical solution to describe the different, what would happen in, different relative motion, what an observer would see in this reference frame and that reference frame, right? So, and then general relativity was to bring in the concept of a gravitational field and equate that to the same thing. And a gravitational field is a mathematical concept that uses vectors to indicate a direction of intensity and or distribution of the force intensity as a force to describe the phenomenon. So it's useful for modeling, but it doesn't provide an underlying mechanism for the phenomenon, right? So anyway, that's what these two theories are about, right? So it's merging abstract mathematic concepts to explain natural phenomenon. So in the history of relativity theory, so this presentation is primarily covers the general theory, but towards the end there'll be some association with the special theory. And to be clear, they are mathematically linked through the equivalence principle, where a gravitational field, the effects of being within the proximity of a gravitational field, are equivalent to what you would experience with uniform acceleration, according to the math, right? So for the general theory, when it was first being established as like the new framework to move forward to explain everything, um, they had to present like some experiments, some validity for relativity to overcome or whatever, right? So they have the perihelion precession, and the deflection of light by gravitational waves and gravitational redshift. So these are the three core things that they say are what proved relativity and what was like the tipping point for, this is more than just a theory, and these are, this is what we're doing with physics moving forward, right? So we're going to go over the experiments put forward to give confirmation for these, right? And before we begin, sorry, did you have a question or something? Someone's mic was going off.
Yeah, I'm sorry. I was testing the overlay in the stream. My bad, dude. I didn't know you noticed that.
Oh, I got you. Yeah, you're good. Okay, so before we begin, we're going to go over a couple of prerequisite terms so we can get the terminology down and get the definitions defined and all that. So a lot of these measurements are done in arc seconds. So define what that is. If you look at a protractor, and you have you look at the distance between 1 and 2 degrees. If you were to break that down into 60 sections, you would have um, 1 arc minute per section, right? And then if you break each minute into 60 seconds per minute, you would have 3,600 of those sections. So you can break down a fraction of a degree when you're talking about something in the sky to 1/360th or 1/3600th of a degree. And then for the milliarcs and microarcs, um, those are typically done with what they call, like, satellites and stuff like that, where there's no atmosphere, refraction, and all that. So when they get with those measurements, that's what they're talking about with that. But it's the same scale, just applied smaller. So, um, so more prerequisites. So we have some more terminology we're going to go over. So space-time, metric, tensors, geodesics, and transformations. So the geometry of space-time is described by a mathematical construct called a tensor. Basically, it's just a way to describe a coordinate system. Um, so it's just defining the boundaries of space-time, essentially, just wrapped up in a neat package. So with that framework, you can use it to describe a Cartesian coordinate system. Let's see. And so for the space-time coordinate system, they just added the time axis to the coordinate system. So X, Y, Z, T. So they put the time axis perpendicular to the x-axis. So your x-axis will be your axis of direction, and then the time axis, they sometimes refer to it as the world element or line element or world lines. That's what they're referring to. It's like a hypothetical axis that's perpendicular to your x-axis. So, what's the usefulness of this type of mathematics? How does it apply? Is it real? What does it mean? Who uses it? So, in the case of engineering, say you wanted to describe an I-beam, for example, you could describe any point in this I-beam um, with tensor calculus using using those metrics to define the coordinates of the I-beam, and you could show a relationship. So say you wanted to say how much stress is the I-beam experiencing at this point compared to this point, and you could express that entire relationship, and you could impose conditions on the coordinate system. So you could say, like, it has this much weight on it, so it's experiencing this much stress. It's made out of this much material, so it has this much resistance. It's exposed to this much heat. Blah blah blah. So um, you can really get specific with the math and the variables and stuff, and it has real practical application that you could use to apply to describe things. So for some more metrics, for some more terminology, we have the Schwarzschild metric that's used to describe space-time outside a spherically symmetrical, non-charged, non-rotating mass, such as a black hole, which is typically what they use to describe space-time curvature due to the due to the mass of an object. It describes the space-time curvature due to the mass of an object and the motion of another massless object traveling through that curvature of space-time. So when an object is traveling through space-time, I forgot to cover this in the last slide, it's traveling on a geodesic, which means it's traveling in a straight path. And then space-time is obviously curved due to the intensity of the gravitational field. And when an object is traveling on that, on its respective geodesic, it's actually traveling along the curvature of space-time that's influenced by the gravitational field. So that's what they would use to describe a stationary object and something traveling through it like that. So the Kerr metric would describe, which is basically the inverse of that, where it describes two bodies in motion that have charge potential and all that. So it just and the reason for that is energy is equivalent to gravitation and all that in space time, or in Einstein's metrics. So if it has rotation or charge or whatever, it's going to have a different type of amount of curvature for space time. So that's the difference there. And then they got the FWR metric or FRW metric, which is for describing the large scale framework of cosmology and all that. So just like when you're talking about different scales of the universe, you can insert a different metric. Is basically all it is. It's basically a plug and play system where whatever you need to describe, there's a tensor already made for you, and however you need to apply the laws of physics, there's a tensor made for that as well, and you just combine them all conveniently. So you get into your curvature tensors, which explain how space-time is going to curve in proportion to the conservation laws and stuff like that. So everything is going to be explained through those. And for spectral shift and spectrographs, When you're talking about spectral shift readings and red shift and stuff like that, what you're looking at, or what, a good example of that would be, imagine you have a telescope here and there's a light or a star here. You're looking at the starlight, it comes into the telescope, it hits a prism, gets split into a rainbow so you could see it, and you're looking for slightly more red in the rainbow or slightly more blue. Very simple concept to grasp with that. And then they correspond those colors with motion, right? So if you're seeing more red shift, they're going to interpret that as something moving away from them. And if they see more blue shift, they're going to interpret that as something moving towards them. So there's a quick video here that I'm not going to play. I'll just briefly explain it on the Doppler effect and how they interpret that with the shifts and whatnot. So we have a stationary observer here. We have a moving car here, and it's honking its horn. So the sound waves are coming towards the observer through the medium of air, which is water vapor and oxygen, and those waves are vibrating right in the medium, and it's also being compressed by the medium that it's traveling through, and that compression is causing that high pitch that the observer hears as the car is going towards it. And that mechanism of causing the high pitch is facilitated by that medium, right? And then as the car moves away, the waves expand and they get that low pitch. And again, the medium, the density and everything of the medium is what's facilitating how how high that pitch, how you get that and how low it gets and all that, right? So the wave interaction with the medium is what produces the interaction for you to be able to discern the difference in relative motion. So when they apply that, they're applying a similar concept to starlight, right? So the red shift would be the car moving away from you, and the blue shift would be the car coming towards you. So for standard observational conditions, when looking at objects in the sky with a telescope, we have a quote from McRoberts from 1995 from Sky and Telescope magazine, who says, "Viewed at a high powered from a bottom of our ocean of air, a star is a living thing. It jumps, quivers, and ripples tirelessly or swells into a ball of steady fuzz. Rare is the night at most sights when any telescope, no matter how large its aperture or perfect its optics, can resolve details finer than 1 or 2 arc seconds. More typical at ordinary locations is the 2 or 3 arc seconds of viewing or worse." So there's the range of the optical or average viewing conditions. So if you remember back to the arc seconds here, the fractions of a degree for the arc seconds. So on average, they're saying you can see like 2 to 3 of these bars. And then a lot of the measurements that we're going to be looking at are actually, sub 1 arc second or, 1 arc second, right? Let's see here. Okay, so to get into the proofs that they put forward for the general theory, we'll start with the perihelion precession with Mercury. And there's nothing too fancy here. The previous Newtonian theory of gravitation that they were using to explain the solar system apparently was unable to predict under the Newtonian framework at that time was unable to predict the perihelion precession observed by Urbain Le Verrier over the course of like 40 years. And then he mathematically extrapolated that if the precession continues over the course of a century, Mercury would precess by 5,600 arc seconds. So going back to that scale again, 5,600 arc seconds would be about a degree 0.25. So a degree and a quarter. They're saying over the course of 100 years, Mercury will shift in the sky by a degree and a quarter. And Newton was unable to explain that to the full degree. He could only explain 5,557 arc seconds per century, and Einstein was able to come up with the full effect. With the concept of space time curvature and gravitational fields rather than mass attracting mass. And so let's see. There's nothing too crazy there. It's just a calculative prediction. So to give a representation of what that looks like, I drew this on paint. So here we have the sun. Here's the equator of the sun. Here's Mercury. Let's say every year that it goes by, it just moves up slightly. So over the course of 100 years, it moves up by 1 pixel. And Newton's theory was only able to explain a half pixel shift, while Einstein was able to explain the full pixel shift of Mercury, if that makes sense. All right.
I don't
And
know if it's just if it's just me, or is it unstable internet cutting off your presentation? Oh, it's back now for me. Was that just me?
you sounded really laggy when you opened up and were talking, so it might have been just you. Is it good on everyone else's end, Shane?
No, I just got an
No, it's
unstable internet myself right now.
yeah, me too.
Yeah, it's definitely my internet.
Yeah, it's spotty for
Mm,
me too.
Okay. Let's see.
It's not terrible though, dude. It's not terrible.
Mm, yeah, so this is just from my cam, so I can change it to a regular presentation. Well, it's from my cam quality though, so like I don't it's already just gonna be 1080p, I think. So I'll change it to the presentation type and lower it. So how's that? All right, cool. Is it clear enough? All right, cool. Sorry about that. I apologize. Thank you, Dave, for clearing that up. All right. So let's see here. So picking up. So for Einstein, so for the perihelion precession, this problem or whatever so called was known about for a while. In 17 years prior to Einstein's explanation, a man named Paul Gerber came up with with a solution and a mathematical equation to explain it, but just under a different mechanism. His mathematic equation was representative of saying that that the disturbance was caused by a perturbation of a gravitational wave, and the speed limit of that wave was set by the ether, and that was then they had already moved on from the ether, so they they his explanation wasn't accepted as a viable explanation for Newton. So Einstein came along and used the exact same equation and just changed two symbols in it, the T symbol here. So what Einstein's contribution to the equation was is he said instead of taking the speed limit for c, all we need to do is take the total time of the orbit, like the time, right, and then just contract that, and with that contraction we can make it meet c to get the prediction. So that's all he did, is like this capital T and this lowercase t, that's all the difference he did between those, is he just contracted the coordinate system to meet C. So that was his mechanism, and that was viably accepted. And then when called out for this plagiarism, Einstein's response he says, how could I have stolen from Paul Gerber if I have never seen his work? Just trying to downplay it or whatever. Even though he has a long history of plagiarizing things. And like, for example, prior to his 1905 publication of Special Relativity, he says that he had, the way that he talks about the Michelson-Morley experiment is like he organically heard about it on his own, and he just decided to come up with the theory, or based on that in the moving of dynamic, or the electro the movement of magnets in capacitors, right? It's like that was his thing or whatever. But a couple years before he published that, he wrote to his wife in a private letter stating that he basically was going to study Lorentz's ether contraction explanation for the Michelson-Morley experiment and moving bodies and magnets and all that. And and he was really interested in it, and he was gonna get back to her. And then a couple years later, boom, Special Relativity comes out, and it's based on Lorentz transformations and adheres to Lorentz symmetry and all that. So, and he gives no credit to Lorentz in his published papers for his special theory. So, like, taking him on the face value of, did he just rip off Paul Gerber's explanation? Like, you'd be the judge. But yeah, these equations are identical, and the explanation is only varied by accepting the fact that the time would, it can vary, right? That's all they changed to facilitate the mechanism to describe the perihelion precession. So let's all right. So for the Schwarzschild metric, so again, after the Paul Gerber stuff, um, using the Schwarzschild metric, the perihelion precession was also derived. And I kind of wanted to give a little preface on the Schwarzschild metric and talk and just kind of showcase how that works and where they, what they're doing with this equation and what they get out of it. So again, with the Schwarzschild metric, they're imposing ideal conditions where they're like, for example, with the sun, they would say it's stationary, non-rotating, has no charge or nothing like that. And then Mercury has no weight and it's traveling in a straight line that's curved due to the sun's gravitational potential based on the conditions imposed on it with the metric used to describe space-time. So to break down what all this means here for the equation, we got the space-time interval. So this ds squared, this is the space-time interval, which describes the distance between two events. And it basically defines the geometry of space-time. And we have this little piece here, this 1 minus g or 2 gm over rc squared and all that. So this factor is used to describe time dilation in gravitational redshift experienced by an observer in a gravitational field due to the curvature of spacetime. So it relates to the frequency of light. So when they're looking for a frequency shift or uh, redshift and all that, and they correspond it to a certain frequency and whatnot, like they get that out of that equation. So dt is your time coordinate, and r is going to be the change in the radial distance between two events in space-time. So it's just establishing a coordinate system as well. And let's see, this one's going to be the factor reciprocal of the above describes the gravitational effect of the two coordinates. So it's just describing that stress relationship, like I was saying earlier, how you can have two events and describe the relationship between them. Your d theta represents the change in the polar angle. So it's just basically calculating angles for everything, between two spheres. So the top of the sphere and the center and all that. So that's really all they're doing with it. Pretty straightforward with the rest of that. And I already covered how they, impose their ideal conditions for it. So when they get their calculative results out of that metric, like that's what they're doing it, or that's what they're doing with it, and that's what it means to calculate with it and get answers out of it or whatever, right? All right. So for the perihelion precession, um, there's lots of explanations for what could be going on in the sky. Is this calculative answer an actual proof of the theory? No, it's not. And everyone already knew that. So they were just trying, so to continue on, there was additional supplemental evidences that had to be put forward for the theory. So it says, "Hey Shane, you might need to reshare or write or reconfigure OBS." Um, Mrs. Tribune says that she's not able to see what we're seeing.
What do you mean? No, it's fine. You were showing that last thing for a really long time, though. Maybe she thought, like, because I thought maybe you didn't know. It was that, like, the math numbers going over and over and over and over again for a while. Like, your slide now is visible to everyone, so I don't know.
Oh, okay. Yeah, I'm on a different slide now. I'm on the deflection of light rays. Is that what you see?
Yeah.
Oh, okay. Okay. Never mind. My bad. Okay. So the next supplemental evidence put forward is the deflection of light rays. So we're going to get into gravitational lensing and all that. Okay. Yeah, we're good, Shane. Thank you. So the deflection of light rays. So let's say we have a star here. We have a giant celestial body here. We got our gravitational field and our mathematical description of the forces of that gravitational field and the distribution of that field and how it impacts the space-time coordinate system. And based on that, a photon traveling in a straight line behind this sun will actually be traveling along the curvature of that space-time coordinate system, and we'll actually be able to see it, and then it'll be as if it were placed here. So when they talk about gravitational lensing and that and the deflection of light rays and with the Arthur Eddington experiment, that's the concept of what they're talking about. So here we have this gentleman, Arthur Eddington, who is credited for finding the first positive evidence of gravitational lensing. So this is Arthur Eddington, British astronomer, who led an expedition off the island of Principe off the west coast of Africa during the total eclipse of 1919 during May 29. The purpose of his expedition was to determine the accuracy of three theories regarding gravitational influence on starlight. So this was the Newtonian theory. So the prediction of starlight displacement was 0.87 second or arc seconds, and Einstein's theory was 1.75 arc seconds. So basically double that of Newton's predictions on how much starlight would have to move due to a gravitational field. And this was going to differentiate between, the concept of mass attracting mass and a gravitational field affecting space-time, and then something traveling in a geodesic having its path altered traveling on that curvature of space-time, because space-time has to be a physical mechanism. So there's also a lot of contention, real quick, to get into a sidebar. There's a lot of contention about, you ask somebody what is space-time, and they either don't have a description, or they'll say, it's the fabric of space, it's the fabric of the universe. It's an abstract concept and whatnot, right? Well, the truth is that it is an abstract math concept, but it has to be given physicality for people to accept it, at least back in the day, before everyone, because the previous framework of interpretation was the ether, and everything is mechanical in that framework. So everything is pressure mediation facilitated by vibrations and vortexes and stuff, right? So everything in there is, connected, so to speak. So this idea of nothing being there and then nothing, like the abstract description of it, conforming, and describing reality, had to have meaningful experimental evidence. So this is a big step in proving the difference between, hey, this is just some blank sheet math where we can swap in different stuff and say whatever we want. Like, these are actual real effects and blah, 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 right? So this was going to establish, like, the actual fabric, right? The fabricity, if you will, of the universe, right? So with these two predictions, this was going to be the deciding factor. And then in combination with this, there were gravitational redshift observations, but those aren't talked about in the mainstream narrative. But in tandem with this starlight displacement observation, there was a simultaneous redshift observation that we're going to get into in the next slides. But for now, we're going to stick to the starlight displacement narrative. So this is just going to cover Eddington and the starlight displacement narrative moving forward. So the official narrative is that that Eddington and his boy Cromlin set out to their two respective places. Cromlin went to Brazil. Eddington went to Principe, and they both had 16 slides. So Eddington's slides, none of those were good. Only two of them turned out to be good. And then his boy Cromlin, they say, due to a temperature differential when the eclipse happened, that his apparatus contracted, and unfortunately, due to that contraction, his measurements were not accurate. So they can't give any good predictions out of that, or any good readings. So they don't use any of his 16 photographic plates. They're all rendered useless. So the only surviving artifacts at this time are two plates that Eddington examines on the spot and gives a quick analysis of them, and he thinks that these two are going to be the ones that give the positive confirmation. He writes a couple of people before he gets back, explaining all this to them about the two plates and whatnot. So that's the story moving forward, is that there's these two plates that give this successful confirmation of starlight displacement. Now, keep in mind, when most people think of starlight displacement, they say, like, imagine this is the sun. Well, so this is the sun right here, and these are different stars. So when you think of a gravitational field and displacement, you think that the gravitational field will displace, stars from, like, all over, right? Because the field's massive, right? So, like, if you look at the gravitational field model of the solar system, the gravity well of the sun and all that, and the planets, like, it, the well is the whole solar system, right? Basically. So you would think that there would be more displacement, in, like, close proximity to the sun and stuff, right? So what actually happened was, they say that they only saw displacement within the solar limb of the sun. So we'll get into that as well. So we got two photographic plates, and we have displacement in a very specific area of the sun where there's already alleged to be a medium and stuff. So 6 months after the observations that Eddington took when he got back to England, and they did their analysis and stuff, it turns out that they couldn't use two of the reference plates either. So the before and after pictures that they were taken for the comparison, so they had to use reference plates that were taken a year earlier, that were made of a different material, and taken with a different setup and all that. So they had to come up with a way to, convert and all that. So after Frank Dyson Watson contributed to a statistical analysis, they figured that they got enough displacement to give the Einsteinian prediction. And on November 6th, this is where the Royal Society and Royal Astronomical Society got together to give their successful confirmation of Eddington's observations, in saying that, the Einstein's theory was confirmed. So I go through the transcripts here for the next couple of slides, but it's kind of dry and boring. So I'll just kind of summarize the I'll just kind of summarize them here. So, Sir Joseph Thomson is the president of the Royal Society, and he opens the meeting by saying that Eddington made a successful confirmation, and Einstein's the man, and he wanted to give everybody a high five. And then Eddington chimes in, and he's like, "Yeah, thanks, it was great." He gives them a high five. He gives a couple other guys high fives, and there was he raises a point about the because of the solar limb situation. So he just tries to kind of preface about the uh, the atmospheric conditions of the sun, so to speak. So on the solar limb of the sun, they assume that there's a magnetic field and and an electric field and a plasma situation going on. So there's a medium there, right? So to separate any sort of displacement from these various mediums and stuff like that would be a high point of contention because this is where the only stars were displaced. So Eddington makes a little preface here saying that the what they know about the sun or whatever that couldn't possibly explain it. The sun's atmosphere would have to be way more dense or whatever, right? There's a couple of pictures here of the slides. We have so going through the transcripts again. So this guy, Professor Alfred Howler, chimes in, and he talks about what does he talk about real quick? So yeah, he gives a brief summary on the spectroheliograph analysis. So this is in regards to the redshift analysis that we're going to get into here in a bit. That was going on in tandem, and he's talking about the two gentlemen that were doing observations to establish a redshift, to establish an actual cause and effect relationship, right? Because not only if there was going to be a displacement, there also has to be a frequency shift if there's going to be an interaction with space time, due to the gravitational field and all that. So there's going to be a frequency shift. So there's going to be some redshift in that. So that's gravitational redshift. So they had people looking for that as well. And this guy makes a reference to that, and he's saying, "Hey, we've even been using spectrums of Venus, and they're showing no displacement. So like, I don't know, we should maybe like look into this a little further." So this guy like raises a little eyebrow at as a little critique to it. This guy chimes in favor of it. And so this guy talks about the atmosphere situation and all that. What they were talking about with the solar limb and the displacement. I'm sorry, with the redshift observations. And he's like raising some questions too, but he's like, congratulations on the successful confirmation. It's all good. So not giving like too much resistance. And so this guy, what he points out is really key to the issue here, because this in tandem with with the knowledge of the gravitational redshift observations that are absent from this um, successful confirmation announcement. Um, Dr. Silverstein says this, and I'll read this here and go over what it means and break it down. So it says, but in spite of what the president said, I believe this result to be essentially an isolated fact. There is a deflection of light rays, but it does not prove Einstein's theory. It cannot logically be deduced from his theory as a gravitational effect in absence of the spectroscopic results. And as far as we know from St. John's and Evershade's observations, the predicted redshift of the spectrum lines of the amount exceeding almost 100 times the probable error of modern spectroscopes, as Professor Fowler has just told us, is not obtained. And Professor Lindman's attempt to explain the obstinate nullity of the effect by the motion of the luminous gases in the line of vision is not satisfactory. For St. John was well aware of such complicating circumstances, and therefore purposely observed as many as 43 lines at the sun's center and as many as 35 at the limb. Now we cannot well assume that the gases move everywhere towards or away from us to suit Einstein's theory, i.e., just to compensate for his theoretical shift effect. As I have already pointed out on another occasion, if there is no spectral shift, Einstein's coefficient, which is described by spacetime curvature, so his G subscript UV is his spacetime curvature, which is entirely responsible for it, must be unity. So if there's no curvature to interact with, or if there's no redshift observations in tandem with this, then you can't establish that there's a curvature of anything that's traveling on. This is what he's saying. So, which is entirely responsible for it. It must be unity. And if we go back to the differential equations, Einstein's field equations, we see once that the coefficient of his well approximate solutions become unity at the same time, and he gives the equation or for how they relate length and time or time and what is it? Time and distance, how they're intertwined, so that the world element reduces to, and then he gives the equation there uh, for saying basically it reduces to zero. So earlier I was saying they take the hypothetical time axis and they make it perpendicular to the direction of motion. So he's saying if there's no direction of motion, then there's no hyperbolic contraction relationship between the curvature of space time and the curvature of space um, to proportionally meet c. So if that's not the case, if there's no redshift and there's no curvature and like none of this is real, so he's saying that all this just reduces back to nothing. And since the equations of motion are always given by, and then he gives the imaginary number equation equals zero, we ultimately see that the spectral shift is absent. Einstein's theory not or not only does not Einstein's theory not only does not give such refinements of planetary motions as in the secular motion of a perihelion, but not even in the ordinary Newtonian or Keplerian motion. In short, the orbits of the planets would be straight lines and the planets would move along them uniformly in spite of the sun's presence. The theory stands or falls on the correctness of the results of Evershade and St. John. So again, that was that cause and effect relationship with the curvature, with the frequency. So back to that equation, how you can get the frequency shift out of that in tandem for how much space time would have to be curved to facilitate the displacement distance, right? So all of that, you can get these predictions out of this equation, and they weren't matching observations by these two men, St. John's and Evershade, who were taking spectroheliograph observations. They were doing the spectral readings, and they found that they could use Venus transits as well throughout the year, so they didn't even have to wait. Well, I'll just keep reading. He actually covers that. Sorry. So we're all caught up on that. So it is unscientific to assert for the moment that the deflection, the reality of which I admit is due to gravitation, in this sense that I declare that it a moment ago to be an isolated fact. The discovery made at the eclipse expedition, beautiful as it is, though not in this circumstance, or does it prove Einstein's theory. We owe it to that great man over there, pointing to Newton's portrait, to proceed very carefully in modifying or retouching his gravitational laws. This is by no means defending blind conservatism. The spectral shift required is perhaps 100 times, but certainly not less than 40 or 50 times the error of modern measurement. The solar spectrum can, even in this country, be observed many times a year, and the matter can thus be decided without having to wait for an equally advantageous eclipse, or having to wait centuries for an eclipse. If the shift remains unproven at present, the whole theory collapses, and the phenomenon just observed by the astronomers remains a fact awaiting to be accounted for in a different way. So that was his analysis of everything so far. So before we continue on, does anyone have any questions? I know we've been over a lot of concepts, and I kind of forgot to stop for a second. Does anyone have any questions or anything? All right, cool. We'll continue on. So, in response to what Silverstein says, Eddington's response is one word in reply to Dr. Silverstein. When a result that has been forecasted is obtained, we naturally ask, what part of the theory exactly does it confirm? In this case, it is Einstein's law of gravitation. It is not necessarily his theory that is confirmed, with the underlying assumption that ds is a quantity measurable by clock and scale. There still remains the question of the intermediary of what ds is. So like what the fabric of spacetime is, right? Is what he's saying there. Which must be tested by the Fraunhofer lines, and the Fraunhofer lines are in regard to the spectral readings. So when you look at let me go back for a second. So yeah, that's way back. All right. So your Fraunhofer lines are going to be right here, like these displacement lines in the readings. Your emission lines, that's what they used to call them, Fraunhofer lines. So when they're looking for those spectral readings to correspond to a cause and effect relationship with the description of a coordinate system conforming to meet C, They're looking for that relationship where they can extrapolate from from the spectral readings that, oh yeah, light did change. It did interact with the gravitational field, such as predicted by the equations that describe it, right? So Eddington's just claiming here, like, hey man, it's all good. Like we got a successful prediction. Like let's not press the matter. And I didn't include this in the presentation because I'm super lazy. But Eddington wrote a letter to Hermann Well, a Swiss mathematician, 6 months prior to the Eddington observations, where they had actually been those St. John's and Evershade gentlemen had been doing gravitational redshift observations for months prior to the eclipse, and they consistently got nothing corresponding to what would give an agreement with Einstein. And Eddington was super worried about that. He reached out to Wells saying, "Hey man, you got this new theory coming out, this new unified theory. We're having this gravitational redshift problem. Einstein's theory is not successful in that. St. John's and Evershade aren't willing to play ball, and it's kind of putting it down. They're being kind of downers to the group, and maybe you can help us out with your theory." So he was already reaching out for an explanation. So like the way he downplayed it at this conversation, as if he didn't realize the significance of what Silverstein was saying is like really disingenuous. And this can be read in a paper from John Earlman and something Gilmore on the redshift analysis or something like that. I'll have a link for it later. But sorry, I forgot to include that. But just a short history on that in Eddington. So he was already looking to jump ship because Einstein's theory was already mathematically failing, and obviously with the special theory failing with the different interferometry tests that were coming out showing a varying speed of light, it was getting hard to co-opt all these things. So they had to really rush this theory in, and Eddington was starting to feel the heat of that. So November 7th, the very next day, the British media and U.S. media successfully announced that Einstein was the man, and Eddington proved his theories and all that, and the starlight displacement. So now, nowadays when people are talking about starlight displacement, like that's the full extended story of it. That we don't really know about. Like most people conceptualize. I know I speak for most people, but the way that I conceptualized this gravitational situation before I looked into it is that there was starlight displacement, within like the proximity of the sun, not within where they already assumed there to be a medium or anything like that, and like such a minuscule displacement and all that. So here's a couple of analyses of the Eddington observation and subsequent observations done after. So this is from H. von Klubler, 1960s in Vistas in Astronomy. It says it should be noted that the deflection predicted by Einstein in 1916 was very small, being about 1.7 seconds of arc of a ray of light at the edge of the sun and inversely proportional to the radial distance of the center of the sun, since no star for which the measurements were made during the 1919 eclipse were within two solar radii of the center of the largest, or, within the two solar radii of the center. The largest deflection that would have occurred to the theory would have been less than zero point 0.8 seconds of arc, which the theory, or I'm sorry, which for the 343 centimeter focal length of the telescope used by Eddington would have corresponded to about 0.01 millimeters or 0.0003937008 inches on the photographic plate. So the effect measured and seen wasn't even so remember Newton's prediction was like 8.7 or 0.87 arc seconds. So like the prediction was even closer to to Newton's displacement than it was, but again with the mathematical corrections from Frank Dyson Watson and the successful confirmation by all these prestigious men and the media and everything, like they just moved forward with this story, like they just rolled through and saw some actual displacement of anything. So this is Dennis Sima from 1967 in a book titled Einstein, the Man and His Achievements. The first attempt to test Einstein's prediction was made by British expedition led by Arthur Eddington just at the end of the Great War, at a time when it was considered very striking that a group of British astronomers should attempt to test a theory proposed by a German. The results of the test were claimed as a triumph for Einstein, and his worldwide fame dates from this event. Ironically, enough attempts have been made at later eclipses suggesting that Eddington underestimated the uncertainties inherent in such difficulties of observations. And even today, there's predictions. Einstein's predictions have not been tested with the precision one would wish. So, going not to dwell back on the history of the Eddington observations, but there was a lot of problems with it. So, like I said, they chalked that one guy's entire observation up to a temperature differential and say that they couldn't even use that. So there was just a lot of stuff going on, and then so subsequent observations haven't gone well either in terms of providing a successful confirmation of providing or supporting what Eddington put forward. And this is John Maddox, Nature Magazine, 1995. Historically, the most dramatic proof that Einstein was on the right track with his general theory of relativity came in 1919 when Eddington and his associate Cromlin took themselves to the western or off the west to the western Pacific to track the total eclipse of the sun of that year. They were bent on measuring the predicted deflection of light from distant stars lying near the limb of the sun. And as the world knows, the prediction was confirmed within the limits of accuracy for the observation. To general applause, Einstein became a celebrity overnight. What is not so well remembered is that the measurements in 1919 were not particularly accurate. The standard error of measurements was roughly 30%, while the displacement of the images of the different stars in the field near the eclipsed sun ranged from half to twice the deflection that Einstein had predicted. The later eclipse measurements have not been much better, largely because the difficulties in making accurate measurements from the ad hoc observatories that have to be established at the locations where you're going to, be, in that alignment, right? So this is from Edward Dowdy here. So this is a plasma cosmologist. And the reason that some people become plasma cosmologists, this is a highly educated and decorated man who changed his cosmology from relativity theory, former NASA employee and all that, became a plasma cosmologist because when he looked into the Eddington observations and all that, he realized that there was no displacement in the way that he also conceptualized the displacement before he looked into it. When he realized that it was within the solar limb and that there was, a plasma could explain it, that was a big pivotal tipping point for him. And you could find his interview on the YouTube channel called Sky Scholar and just type in Edward Dowdy on the search on their playlist or whatever, and his video will pop up. It's an interesting interview. He wrote a couple of papers on all of that. So just to give one more reference to the sort of displacement. So starlight, you would think that starlight displacement would happen from a big gravitational field all over, but it really only happened within this select area where there's different, could have been anything, right? Let's see. Okay. Okay, so in conclusion, from the mathematics that are used to describe everything, when the experimental evidence doesn't work out, they just don't talk about the experiments. So we went over the gravitational redshift a little bit in regards to that experiment. So they totally prop up this observation experiment as if it wasn't completely undermined by the gravitational redshift observations that were going on in tandem. So so they have no cause and effect relationship for any displacement, if any, and no one really has done any subsequent observations that could back up what they say happened. So to get into gravitational redshift now, we're going to get into those effects. So light and how it's in its interaction with gravitational fields and space-time curvature. So there's different types of redshift. There's gravitational redshift, where the wavelength of light from an object is shifted towards the red end of the spectrum as it travels through a gravitational field. This effect is caused by the fact that the photons lose energy as they move out of the gravitational well. This loss causes the wavelength to stretch to compensate. So remember, the speed of light is always the same. So to compensate for the energy loss, there's a stretching. and the stretching is the amount stretched, like frequency. All of that will be is predicted, from those equations that we talked about earlier. So all of that can be derived from that. So cosmological redshift, so wavelength of light of an object is shifted towards the red end of the spectra due to the expansion of the universe. This is caused by the fact that the universe is expanding, and therefore the distance between the two, um, the source and the observer is increasing. It's changing. So the distance, that relative motion, is causing a stretching, or is causing a change in the wavelength of light, which stretches it, which causes redshift. So that's their interpretation for cosmological redshift. So when they talk about, Hubble shift and everything's moving away from us, and the bread rising or whatever, the raisins and all that, that's what they're referencing. So the transverse Doppler effect. So this is a phenomenon in which the frequency of a wave appears to be shifted towards the source, or shifted when the source and the observer are in motion to each other. Um, so this was so they kind of equate this to like a time dilation effect when they for a certain type of Doppler shift, for a certain spectrum shift in light. So in summary, in general relativity, there's different predictions that can be made due to the curvature of space-time, based on the presence of the objects in it, and the interaction with light, with the interaction with that gravitational field based on the presence of the object, right? So other types of redshift. So let's see, Doppler redshift, so caused by relative motion between the source and observer. So time dilation redshift. So that was, and just that's in more regards to the transverse Doppler effect, or the relative Doppler effect. I forget how they worded it. It's worded a couple different ways, but that's the time dilation redshift type thing. So the gravitational lensing. So that would be an effect in tandem with this redshift. So that would be where there's an actual displacement of that. Let's see. And then so Hubble, proposed that, everything was expanding away, but even up until his final lecture at the Royal Society, he always held that there was a possibility that he was interpreting it wrong, and that the velocity recession that they're observing might be due to something else. So I just thought that would be a nice point to include there. So let's see. So for gravitational redshift, they're in um, back in 1919 with the Eddington experiment. There hasn't been any gravitational redshift to supplement the starlight displacement, right? So they were looking for another way to test this. So in the 1960s, they did the Pound-Repka experiment. Two gentlemen got together at Harvard's Jefferson Tower, a 22-meter tall structure, and had a photon emitter at the top of the tower and one at the bottom, and they emitted photons from the top and at the bottom, and they measured the frequency shift, um, at the top and at the bottom, and they were looking for, relativistic predictions, right? So there's a couple different explanations that are given for this experiment. It didn't give a, if you go to like Wikipedia or whatever and you type in, proof of relativity theory, the Pound-Repka and Pound-Snyder experiment will be on the proof of the theory, but it didn't give a positive confirmation of the theory. And even from the two papers that these gentlemen published, they make note of that. So we're going to read a little bit of their papers before we get into the relativistic interpretation of these experiments as to why people interpret them as giving confirmation of the relativistic theory. So this is from the effect of gravity on gamma radiation from Pound and Snyder. So this was the follow-up experiment from Pound Repka. Same situation, just in a taller building. That's the only difference. So they recap a little bit from their first paper. So they say their first paper was titled "The Apparent Weight of a Photon," and their conclusion from the first paper was that the effect of gravity was as if it was pulling the photon faster, so that it was so like it got there a little faster, and they didn't quite know what to make of that because in relativity theory, the speed of light should be the same and all that. There shouldn't the the light shouldn't change in that way. So they said, so the title was "The Apparent Weight of a Photon." And then so that's what they're referencing here. So they say, "It is not our purpose here to enter the many-sided discussion of the relationship between the effect under study and the general relativity or energy conservation. It is noted that strictly no relativistic concepts are involved here, as the description of the effects of an apparent weight of a photon is suggestive. The velocity difference predicted is identical to that which a material object would acquire in free fall from a time equal to that flight time. So the distance travel time, it's as if it acquired, at 9.8 meters per second squared increase, right? So, and then they go on to try and say maybe the rotation of the Earth had something to do with it, but it didn't. So that wasn't able to give an explanation for it. And then they close on this. They say the view that the local time scale depends on gravitational potential appears to require a coherent source for confirmation. The present experiment is unable to distinguish frequency change and velocity changes. For example, it appears as if experimental comparison of clocks at different potentials would make a useful complementary contribution to the overall status of relativity theory. So what they were saying here is they were unable to establish between relativistic effects due to the interaction of a gravitational field and space-time curvature and relative motion through classical mechanics, and that maybe they should do an experiment with synchronized clocks, which we'll get into the Heffel and Keating experiment as we move on. So with no successful confirmation of the theory alluded to in these papers provided by these gentlemen, how do the relativists interpret this experiment as successful confirmation? So there's a couple different ways, which they're kind of lengthy, but I'm not going to get into all of them. The most common one that they do is they say, where's time dilation at? Yeah, okay. So they typically go with time dilation, but someone generously calculated everything out for me. So if you give them the benefit of the doubt on the gravitational potential in an object and all that, and the shift, time dilation effects would be into 2.7 times 10 to the negative 21 effects, right? And then the pound rep experiment itself was measured in the 2.5 times 10 to the minus 15. So any time dilation explanations would be well outside of well outside the abilities of, the measurable capabilities of what these gentlemen had going on to give an actual explanation. However, you can calculate the effect out, and that calculation effect is, what people generally say, because it can be calculated, they interpret that as like a true meaningful thing, but it's not even within the scope of the experiment to produce a visual effect that would have affected anything. But that is the most common explanation for it. So to give a quick explanation on what also produces redshift in light is the Stark effect and the Zeeman effect, respectively. The Stark effect is an electric field, and when there's electromagnetic propagation going through the field, depending on the density of the field and the direction of the current flow, that will affect the light spectrum, in a way corresponding to, like, if it's going upstream or downstream, right? So it's going to slow it down or speed it up, and so to speak, and that's going to cause a frequency shift, and you're going to be able to get readings out of that. And let's see. So the Zeeman effect is the same thing, but with a magnetic field. So the density of the field is going to be um, it's going to dictate what kind of effects you can, the strength of the effects that you can get out of that. So these are known effects that produce the same spectral readings that they're reading, right? So when they take emission readings and they're like, hey, this could be this is this gas because this line's missing, so it means that this element is in the atmosphere or whatever, right? So when you're looking at when light's passing through an electric field or a magnetic field, well, what can happen is that there can be a splitting effect, so to speak, where their end result was it'll just create lines where, it'll make you think like, hey, this element's present in the readings, but it's not, or it'll make you think, oh, it's shifted this much red because of, this factor, but like you didn't account for the magnetic field or something like that. Like it can produce all of those effects. So we'll get into some demonstrations of those by the homie Ken Wheeler, who demonstrates electromagnetic retardation. So when an electromagnetic wave propagates through a field, it experiences retardation. So that frequency shift where it gets stretched or compressed or expanded and all that, that is electromagnetic retardation. That's what that's called. So Ken Wheeler has an excellent video on that I'm going to play through. Let me reshare this to make sure that the audio can come through. Actually, I think I shared it right. Let me know if you can hear the audio on this real quick, Shane.
I've made so many
Yep.
discoveries in magnet.
Good. Okay,
Roger.
solid. Okay. So we're gonna watch a little demonstration of redshift and relative motion shift with a magnetic field, demonstrating the shift based on a magnetic field. So you got the timestamp here. Just give me 1 second. All right, take it away, Kenneth.
Slew. But how can I shift that relative motion to the disparity of the electricity, i.e. light, which is a coaxial circuit, transverse electrical magnetic?
I'm sorry, to preface real quick, he's got a neodymium magnet here under this ferrocell. And what he's looking at is a holographic projection of the ferrofluid with in between the lenses there. So he's got like a what do you call it, like a castor oil type solution, right? Like just an oil lubricant, and then some iron filings where you can also use a drop of your blood and use the iron in that, which I think that's what he uses in that. So that produces a
Did you
hologram of the magnetic field, and that's what we're looking at. So sorry, go ahead.
what did you say goes through the magnetic field and experiences the EM retardation? A photon?
Any electromagnetic propagation. So like
Okay, anything.
yeah.
Okay.
Yep. So we're actually going to see what that looks like in real time, right? So I'll let Ken take it away.
Longitudinal dielectric. Let's show you phase shift. Now look closely and I'll explain it. You see how this is blue now? As it was approaching, it went to blue shift. If I move it away, let's just look at this one pole only. Let's ignore this pole over here, okay? You notice that this red shifted now? Let me move this closer to a person over here. Let's say there's a person on a little planet over here, and this is a star. Okay, now it's red shifted. Let's move the star closer to this person over here. You see how this blue shifted? Let's move it away and watch this blue, which is bluish green, but it's still blue shifted, turn to red. Red shift. Blue shift. We're only looking at this pole over here. A second. I think I had a little power outage there. There we go. Blue shift. Red shift. Red shift, moving away from this relative point. Now let's take a look. Let me check my power connection here. Let's take a look at the other pole. 1 second. There we go. Sorry about that. Let's take a look at the other pole over here on the right side. Let's orientate my magnet exactly. Okay. Let's wait for it to appear. There we go. Let's take only a look at this. Blue shift relative to this person over here. Let's say this point over here. Blue shift as it moves away relative to this point. We have red shift. You notice how it shifted to the red? Now watch it shift again. Remember, only looking at this pole on the right side of my finger. Okay? Red shift, blue shift. Red shift, blue shift. Inverse to the other pole. Look closely. Nothing has changed other than disparity of EM retardation. It has nothing to do with space. Has nothing to do with time. It is EM phase shift disparity or EM retardation.
So the frequency of light that's propagating in there is being affected by the magnetic field, and if it's traveling with or against it, that frequency shift is producing a color what's it called? Color shift. So that's why you're seeing that red and blue shift uh, switch there. That's what's producing that electromagnetic retardation. So if there was like an experiment that somebody could do where they could have a space-time magnet over a ferrocell and produce something like that would be an awesome way to demonstrate a cause and effect relationship with light in a medium or a or an abstract hypothetical description of a medium that may or may not be interacting with a photon, with an alleged photon. Sorry, was there a question? I heard someone's mic going off.
doing the ends of each one. Have you heard your opponents to this specific video from
Well, I'm sorry, say that again.
him? Have you heard people that strongly disagree with his interpretation of the phenomenon that we're witnessing there?
Oh yeah, so even if I played the video on mute and like we didn't hear anything he said about how a magnet works or his interpretation, the effect still persists. What he demonstrated, even though he doesn't know it, is the Zeeman effect. That's exactly what would be what's already like established as something that would happen. So this would be like a demonstration of the Zeeman effect, right? The electromagnetic retardation causing a phase shift in light.
What?
Yep. Yeah, so yeah, I usually actually preface that because a lot of people don't like Ken Wheeler and they're like they hear Ken Wheeler and they're like, "Oh my god, no, I can't." So I usually preface that. So thank you for bringing that up. I forgot to preface that.
They hate on that video right there. They really try to say he's false analogy. You know, like I think he tries to apply that to the redshift out in stars in space, and they don't. A lot of people don't like it. I don't know about it. I'm a reporter.
Well,
Thank you.
yeah, no. So that's really interesting because actually recently Witsit pointed out an article where an astronomer was saying that they made some prediction and they were off because the star's magnetic field caused the redshift, which was a glaring omission because they don't really talk about the effects of like because all these planets and stuff have magnetic fields and whatnot, right? Or like most of them do anyway, but they never really talk about that or make any sort of corrections relative to uh, what that would produce. So they attributed the whole effect to the planet's magnetic field, and it's like, oh, dude, so are we going to reanalyze everything now, or just this one time? Um, yeah, like that's why they don't want to talk about it because it's too much extra stuff for them to deal with. Because a lot of like so-called relativistic effects, the behavior of light, basically, is explained through electromagnetic retardation and just like an interaction with the medium. Like, so they're all inseparable from classical mechanic effects, right? So anything where they're like, oh, there's a shift in the light, it changed. Well, I think that's all facilitated by a medium inherently. So the trick here was to convince people that this shift would happen if you move this ferrocell over nothing or over a so-called gravitational field.
I'd love to learn more deeper about it with you later, but I won't.
What's that?
Obviously, you got a whole. I'd love another time to go over this one thing specifically. I can learn more about it from you, probably.
Okay, cool. Yeah, we can come back to it or something later. So here's a cool video from my buddy Shane who shows this magnetic vortex situation. Oh, sorry, I skipped ahead a slide. So let's see. So there's a lot of speculation on where we live and all that with the block domain wall and the magnetic field and all that sort of stuff. So if you take this redshift situation and turn it sideways and look at it through the symmetry of the magnet this way through the block wall, you could interpret all the effects they're seeing inherently through the magnetic field. That would explain everything. And then here we're gonna play a video from Shane who uh, who illustrates this magnetic field situation, if I remember correctly. And if I don't, that sucks. But we're gonna watch it anyway.
I'm gonna do a quick little recording on this magnetic field map, right? So it's supposedly the magnetic field is the covered magnetic declination. Oh man, this is old. Especially there was uproar after this.
Yeah.
Who are familiar with the black sun model and what
Yeah.
we think the northern lights
Yeah, this
really
is a hot
are. But
minute ago.
anyway, you have this this giant model coming.
So this is a model of our magnetic field vortex and all that. So that's going on, and could produce all the effects that they see and stuff like that. So when they're talking, so later when we get to the Heffel and Keating experiment, where they took flights around the equator going east and west respectively, two separate flights, and their devices go out of sync, and we now know that there's an interaction with the magnetic field and all that. We can, you can kind of start to see that there's other possible explanations than time contracted and space contracting proportionally to meet C. Um, so anyway, so I think that was the overall key point of the video is just to get to show the overlay from bobwins.com. All right. Okay, so the conclusion of the Pound Snyder was inconclusive. Didn't provide any actual evidence for the theory, and there's other explanations for it. So, like they were suggesting that maybe an experiment should be done with clocks so that they could reference that, because a lot of Einstein's theory is built on clock synchronization and what happens to that synchronization due to acceleration and or gravitational potentials. So we have here the yellow is the before and after, the red is the difference, and the blue is the mean. So for their before and after times, basically what happened to summarize here is they had predictions for how much their clock should go out of sync, and all the clocks came out of sync wildly disproportionate to how much that they predicted. So it kind of renders their ability to give viable readings out of it. Based on their predictions, kind of renders it a little useless. Um, so let's see here. So just to summarize here, what happened was the original published data that they published in 1971 or 1970 didn't match the relativistic predictions at all. And then they later republished their work in 1972 with a post analysis and consolidation of the different factors and corrections for different things that they would have to account for their experiment. And they brought it in alignment with relativistic predictions after that. And they didn't include what they corrected or anything like that. This excerpt here was taken from a paper where a guy kind of reverse engineered based on what he thought they might have had to correct for. So, like, the fact that they didn't publish what they did or corrected for is kind of sus. And then also, you can just reverse engineer any, like this guy just worked it out himself to match the same predictions that they got, and so it's just they just mathematically reconsolidated the data to fit relativistic predictions. All they really proved is that moving clocks move out of sync faster than stationary clocks. And to get into what I mean by clocks and atomic clocks and all that, so an atomic clock, when they talk about a cesium atom, atomic clock, all that, right? The cesium has a known decay rate for its frequency. So when its energy is decaying, it's vibrating less basically, right? So it has a known amount of vibration. I think it's 12 billion vibrations a second or something like that. So when it's vibrating at that known amount, it's relatively stable, right? So they can keep it stable. They can by injecting microwave energy into it and having it between two magnetic fields. So earlier, when I was talking about electromagnetic retardation, they can kind of use that electromagnetic retardation to balance out anything that's not in that 12 billion oscillation cycle. And then, so they'll only get an accurate reading from what's in that magnetic field and what's actually oscillating at that 12 billion predicted cycle rate. So they manufacture the synchronization of the clock in the lab frame. So when the clock is stationary and it's not moving, it's still it goes out of sync. It just slower, right? So when it's in motion, it goes out of sync to varying degrees. And that's all they really proved with that experiment. When you get into the specifics of how the atomic clock works, because a lot of people seem to think that the cesium atom or whatever that may be, that resonant energy that's vibrating at 12 billion oscillations a second, that just does that in perpetuity or something. Uh, but it decays, it goes out of sync, in a stationary situation as well. So they have to constantly provide corrections and utilize two magnetic fields to keep everything, going at that 12 billion oscillation rate. And these are the biggest proofs of relativity, guys. Like this is what they're like. This is what they hung their hat on. These interpretations of these experiments as solid evidence. So we're gonna get into gravitational waves real quick. But before we continue, though, does anyone have any questions or anything like that?
I think you should have been a little more sarcastic when you said solid evidence.
Yeah, yeah. Okay, so for the fourth proof, gravitational wave. So it was 1916. Einstein published a paper predicting gravitational waves, saying that there would be, this ripple in space time due to, X, Y, Z, and all that from the gravitational fields, and that this would be something that is measurable and predictable, right? So, insert the LIGO lab. So they devised a giant laser interferometer to detect these gravitational waves. Now, sadly, they could not detect Earth's orbital velocity with an interferometer setup, but they can detect something way smaller than that. And so they built this laboratory here. So this is LIGO. So this is a combination of two observation bases, one in Louisiana and one in Washington, I think. Can't remember. It doesn't really matter. But anyway, the idea here is that a gravitational wave will ripple through, space time, and it will ripple at one lab, and then it'll ripple at the next lab, and they'll be able to get they'll be able to get, like, a confirmation that based on the two observations and propagation time, etc., that it's a gravitational wave or whatever, right? So that's how they're gonna isolate it or whatever. So this is an excerpt from one of their from the first announcement in 2015, I believe it was, or 2016, when they did their press tour of the first confirmation of a gravitational wave titled GW150914. Very sciencey. So here's our boy successfully announcing gravitational waves real quick.
Ladies and gentlemen, we have detected gravitational waves. We did it. Ladies.
All right, so that dude, so that dude was super pumped about it. Very excited. And so a little history on LIGO, real quick, before we get into the gravitational wave itself. We'll look at the credibility of the institution.
My guys, my guys.
Yeah. So the collaboration. So lesser known to people that there was a false blind injection where they injected fake data into the system, and they had the scientists there analyze the data, thinking that it was a real test. So by a blind injection, it's what they did is they had a team had private access to their servers and stuff, so they snuck in and implemented a system where they could inject a false positive detection, and then the actual scientists, not knowing that it was a false positive, would analyze this detection and see if it was see if they could distinguish between basically find out if it was fake or not. Basically it was a control test to see if they could discern whether or not it was fake. And so I'll read here from LIGO on their take on the situation on that little blind injection stress test. So the collaboration knew that the detection could be a blind injection, a fake signal added to the data without telling the analyst to test the detector and the analyst in their analysis methods. Nonetheless, the collaboration proceeded under the assumption that the signal was real, and wrote and approved a scientific paper reporting the groundbreaking discovery. A few moments later, according to plan, it was revealed that the signal was a blind injection. While the scientists were disappointed that the discovery was not real, the success of the analysis was a compelling demonstration of the collaboration's readiness to detect a gravitational wave. So their readiness to detect anything doesn't mean anything at all, and that's a really positive spin on the fact that they have no actual phenomenon to compare a so-called gravitational wave to, and that they could be successfully fooled by a data simulation. So any thoughts on that, Shane?
Aggressively fooled by a data simulation? Nah, it's impossible.
Couldn't happen to
I
these guys.
mean,
They're scientists, for God's sake.
yeah, I think that's fine. I mean, I figured they're trying to test them, like, also to even see if they even notice at all. You know what I mean? Like, not notice is it real or fake, but just, hey, are you asleep on the watch? Did you even notice the thing that you're looking for happen?
Well, no, like, do with
I mean,
it.
they tested them in all ways, right? They
That's
tested them in.
that's auto. Well, no, that's automated. They wouldn't need they wouldn't need a guy to like watch it. You know.
When you
Okay,
Anyway,
okay.
when you
yeah,
played the
you're
clip
good.
and they were celebrated like
Yeah,
they just landed on Mars and like the rover
yeah.
just fell through the atmosphere,
Yeah,
they were like, "Yeah, great!"
it
You're like,
was
"Oh, that's
very,
very
yeah.
believable."
It seemed very practiced, and it also reminiscent of the what was I'm not sure which astronaut it was, but he said that the moon landing simulation would be just as real, and they wouldn't be able to
Right,
tell the
right, right.
difference.
But like,
Yeah,
so they had that announcement
Yeah.
with that crazy emotion with people going, "Yeah," and then later they were like, "Actually, what happened was we faked some data and we wanted to make sure it worked. Congratulations, everyone reacted greatly, but someday we'll find it the real one soon, right?" Like, didn't something like that happen? Isn't that like wasn't it that outrageous?
That's why they built it
Yes.
up because they were so used to fucking rehearsing it. But yeah, I don't know, man. If the blind injection thing, the blind injection was supposed to throw them, like, was it supposed to be outside of, the threshold of what they're looking for? Like, why wouldn't they be fooled by it? Is what I'm saying. Of course they're fucking fooled by it,
Exactly.
right?
But people seem to think that they're not, and that there's like a gravitational wave that they could maybe compare it to or something like that. But this just kind of illustrates that it's all theoretical and nobody knows, and you could fool them with a simulation very easily as it was done. Like they were ready to publish this and go to bat for it, and then like they had to pull the plug on it because like it wasn't real or whatever. And then
I
they had to get the real detection, right? So.
I have a funny story about the LIGO in Livingston. I live near it. I called him up several times, and the first time I called him, I said, "Is it true that the LIGO laser is horizontal?" Like I just mentioned the word horizontal, and his reaction and his answer to me was, you can go to the beach and see boats go over a curve. Now you can't make that stuff up. Like that was his answer. The engineer in the office, that's what he told me.
seems
When
like
I
he's gotten
even
a few phone calls before you, maybe.
yeah, yeah.
Yeah.
I gave no inclination that I had anything to do with flat Earth or whatever. I was just asking about the tube, the vacuum tube, and the laser being horizontal. And he mentioned going to the beach and watching boats go over.
Imagine showing them this
Yeah.
presentation, huh?
How
Yeah,
did you
that's pretty
react to
crazy.
that? Did you tell him that actually the boats over the curve don't prove a ball? Did you even get into the conversation at all, or?
No, I didn't even like go into what he was talking about. I said, yeah, I go to the beach all the time. I'm not even asking that. I'm talking about LIGO. You're what you're over, and he just wouldn't go into it. But I've called
Wow.
twice and talked to two other people, and they were supposed to have like start opening. They call it Science Saturday or something like that. But they had shut it down due to the epidemic. But they haven't opened it
Uh,
back up, and then they were doing construction on a third tube there, another tube that goes in.
All right, so sorry to cut you off. Like, well, I'm gonna continue the presentation. Sorry, we'll pick up on the LIGO afterwards. All right. Okay, so to wrap up here on LIGO, so the successful confirmation of GW150914, they said that this confirmation was done before the system was fully operational after a reboot had been done to the service after maintenance. So it was it was done after maintenance, and the safeguards where they have a system that prevents false positives. That system wasn't running either, so they weren't. So even under those conditions, they were still like, "No, we got to take this, boys. This is our golden goose." So they went ahead and went with that as their big publication for their gravitational waves. And every year, I think they make like one detection or something, or they're publish something and act like they're doing something. But a real quick thing on black holes. So black holes are derived from an event called a singularity, and to describe a singularity, that's a mathematical concept of tending towards or like the difference between like 1 and 0 would be infinity if one could always tend to 0, right? Like 0.1, 0, or 0.01, 0.02, that kind of thing. So it goes to infinity. It's the concept, right? It's not real. At some point, you're going to physically hit that limit, and there's not going to be an infinite tendency towards 0, right? So this is a mathematical concept. So through the Schwarzschild metric and descriptions and all that, they impose conditions on the metrics. When they break the metric, it imposes what's called a singularity, where the space-time curvature folds in on itself infinitely, and it just breaks down all their math, right? And it produces all this crazy stuff where that's where they get like this gravitational potential of a star collapsing and it creates a black hole. It sucks everything into it. And once you get within the event horizon, not even light can escape and all that. So all that comes from a mathematical concept where they've imposed conditions on a metric and then broke the metric and then turned the breaking of the metric into into like a pop culture reference and made a bunch of movies about it. And I'll be honest with you, like I love black holes. That was like one of my favorite parts of being a heliocentrist is that there's black holes in the sky and gravitational getting lost in a black hole and stuff like that was always the coolest concept ever, right? Like what goes on in a black hole, like all that kind of stuff. It's all just based on them imposing conditions on a metric that the metric can't define, and then out of that they tell a story about it, and then they use this gravitational wave prediction to help reify that. And then, so in a mathematical analysis by a man named Stephen Crothers, he shows that how they derive the how they derive the gravitational wave solution. It's actually meaningless because if you transform that gravitational wave into another coordinate system where the medium doesn't have the permittivity and permeability of a vacuum, the speed changes, so it doesn't provide invariant transformations. So it's non-covariant. It means nothing. It's not a law of physics. It's not predicted by anything. The fact that it propagates at the speed of light is only done because it was chosen in a respective coordinate system to like facilitate the illusion that it supports the Einsteinian mathematics and all that. And that was from Stephen Crothers, and there's a link to that I can provide. But that was his analysis of that, and he does a transformation of it and shows the speed propagation changes. So like this whole concept of it matching a gravitational wave and all that is just it's not real at all. It was just chosen to give for them to have the ability to calculate it, right? So really, really unfortunate. All right. So we'll move on now from the gravitational wave detections. Let's see here. What do we got? Okay, so experiments with light. So this is getting into the special relativity side of things. So this was the jumping off point before the general theory and how they hinged them together. I'm sorry, with the equivalence principle and all that. So, but both theories, general and special, are both based on the constancy of the speed of light. So we're going to analyze some experiments with the speed of light and see how those turned out. So with Michelson-Morley, the speed of light varied, and to explain that, they said that there was length contraction within the coordinate system, and because the reading that they got from Michelson-Morley didn't correspond to 30 kilometers a second. So with that, they were unable to successfully confirm heliocentrism. So to say that the speed of light was truly the same, they had to, and that the Earth was truly in motion. Using relativity theory, they were able to say that the apparatus could contracted in the direction of motion, and that produced that variance in the speed of light, which if you reverse engineer the contraction would produce the full 30-kilometer reading, right? So that was their jumping off point for that. And Lewis Essen has a little quote here of relativity theory, and he says, the contraction of length and time dilation can now be understood as representing the changes that have been made to make the results of measurement consistent. There is no question here of a physical theory, but simply of a new system of units which C is a constant, and length and time do not have constant units, but have units that vary with v squared and over c squared. Thus, they are no longer independent, and space and time are intermixed by definition, and not as a result of some peculiar property of nature. So Lewis Essen, the godfather of the atomic clock and big proponent of relativity theory, until later in his retirement, he realized that there was a bunch of inconsistencies with the theory, and that it wasn't logically sound or tenable to as a framework. So he went against it. So this was a quote that he had, describing what was going on. Basically, to turn C into a ruler stick, space and time have to contract proportionally. So that's where you get into the length contraction and time dilation. Those are that's what that means. All right. And thanks, Witsit. So what were we thanking Witsit for? It's been a while since I've done this, so I don't remember some of it. Sorry. So if David Miller results a little, I talk about Miller. Let's see. Oh, okay, yeah. So with the history of interferometry, real quick, Michelson-Morley was redone by Dayton Miller from 1905 to 1925, where he did 5,200,000 measurements with interferometry, where he consistently measured a variance to the speed of light. He actually accurately mapped out the what he thought was just an albeit at a lower speed, at a lower translational speed, but he thought that he was measuring the elliptical orbit of the sun or of the Earth around the sun. So as we see the analemma, mapped over the course of a year, where that discrepancy of the north and the south, they say in the Earth's orbital or Earth's elliptical orbit, when the to complete that, the Earth has to speed up and slow down 4 times a year or 2 times a year, 4 times respectively, to facilitate that motion. And when it's further away, that's when you're getting that bigger arc for the analemma and all that. So he thought that that's what he was measuring, with interferometry. He measured it so accurately down to the day where the interferometer was getting its minimum and maximum dimensions on the fringe readings on the day to the equinoxes. So he was consistently measuring that, but that was through an ether framework of interpretation. So nobody was interested in Miller's readings in his continued showing of the variance of the speed of light. So they chalk Miller up to they say that he didn't know about temperature differentials in his work, and that there's some statistical analysis error with his work, and to not get fully sidebarred on all that. Um, there's there's more repeated effects with interferometry with Sagnac, Michelson-Gale, Ruyang Wang, DeFore and Pruner, lots of other people showing a variance to the speed of light, but we'll get into those in a bit. So here we have Einstein saying, if Dr. Miller's results should be confirmed, then the special relativity theory, and with it the general theory in its present form falls. Experiment is the supreme judge. Only the equivalence of inertia and weight which remain or would remain, which lead to an essentially different theory. Albert Einstein, Science Magazine, 1925. Uh, so that was his thoughts on Miller's work. So he was well aware of Miller and all that. They just kind of downplay it, and they ended up just not talking about Miller until he died. So so anyway, to explain the variance in the speed of light, the special relativity framework is proposed, where they use what's called Lorentz transformations, where they go to a different reference frame to observe a non-variance in the speed of light and explain the variance in the speed of light in the current reference frame through a mechanism of length contraction and time dilation, where the amounts of length contracted and dilated are verified in the new reference frame. So that's what they came up with to get into that, and to show the Sagnac device. So I'm not going to get into interferometry too much because it's already a long presentation, and that's kind of a separate thing. But the Michelson-Morley setup was, 90 degrees, perpendicular to one another on an axis situation. So with the Sagnac, it was a circular rotating device. The path of the light beam was circular in that regard. So they consider that apparatus different, and because it's rotating, they say it's a non-inertial reference frame and all that. So they let it slide. But then through general relativity and the equivalence principle, they co-opt the Sagnac effect, saying that the rotation of the device, the energy of that, is equivalent to generating little pockets of time dilation and length contraction within the device to produce the effects of the fringe shift. And remember, the special theory is linked to the general theory through the equivalence principle. So the relativists have a quote unquote think they have a successful explanation for the Sagnac effect through the metric tensor provided by Paul Lavue to describe the angular momentum on the small scale of a tiny rotating device. All right. So some demonstrations of that. So in 2003, Ruyang Wang did an experiment with a linear fiber optic cable wrapped around a conveyor, or he basically made a conveyor belt out of a fiber optic cable. And what he found was that the circular bits also or that the linear bits contribute to the friend shift pattern, as well as the predicted or the assumed circular bits would contribute to the effect. So the it basically took away the relativistic explanation of the effect, because what Wang showed is that it's not an effect due to rotation or anything like that. It's a directionally dependent effect, meaning that the effect persists when the device was aligned east to west and west to east, and the propagation would go faster going east to west and slower going east to west at the same rate. Let's see, IF Stillwell. So IF Stillwell was where they came up with the transverse Doppler effect. So the relative motion redshift situation that I was talking about earlier at the beginning of the slide. So basically what they had was a big conveyor belt, a device mounted on it that was going to shoot a beam. And then they were looking for redshift based on the relative motion of that. They found it, and then they attribute it to relativistic effects. However, the effects shown can't be uh, can't be distinguished from or I'm sorry, the effects are indistinguishable from classic mechanics effects. So like with an ether effect where you're having relative motion Doppler shift, the effects produced are within that same measurement error. There was a paper by Daniel Gezery who points that out. And to close on what he ends on, so he says, furthermore, it is a little known fact that the classical transverse Doppler effect that is observed in acoustics, which suggest an analog in the classical wave theory, so a medium for light, although no such effect is described in the textbook. So in modern textbooks, they don't tell you that all these effects, that all these so-called relativistic effects and whatnot, are explainable with classical wave mechanics, with a medium and all that. So here's a list of modern interferometer experiments: Silvertooth, Kennedy Thorndike, et cetera, et cetera. So what you'll find is that the interferometers now are tending towards zero, and this is facilitated by the way that the experiments are done to explicitly give a reading that matches the relativistic prediction. And they do this by changing the location of the sensor in the apparatus. They change the medium of the tubes or whatever is that the light is propagating in. They'll either add a gas or change the type of gas, or do it in a vacuum. They'll do some variation of it, or they'll what's the other thing they do? Can't remember off the top of my head. But they change the length of the arms of the apparatus, make them out of proportion, stuff like that. And so changing those factors will give you varying readings. And when they do them in a basement as well, it also affects the reading. So they go well below sea level, and then they go in a basement, in a concrete basement, in a steel building to do the readings, and they get the effect still persists. Like they still get a small reading, but it's just way lower, and they attribute that to tending towards zero, and they say that that's successful positive confirmation of the invariance of C and supports relativity theory and all that. So and all of that was already discovered and figured out by Dayton Miller between 1905 and 1925 through his work with interferometry. So all the effects that they use now to basically hijack interferometry and make it seem like it supports relativity theory, all the groundwork was done by Dayton Miller over the course of about 30 years. So that was cool. So here we have the photon for vacuum propagation. So we have, what is the photon? So we have three equations here that describe the photon, and the frequency of the photon, and its behavior and its momentum, and how they facilitate vacuum propagation of the photon. So we have the classical way to derive momentum. So P equals m times v. So momentum is described by P times v. So mass times velocity gives you your momentum. So that was the classic understanding of it. And the way that they ended up describing the momentum, the physicality of the photon, so to speak, through this equation, they have P equals delta equals h kV, which is the reduced Planck's constant times k. So here P P is the momentum of the photon, delta is the wavelength, K is the wave vector, H is the Planck's constant, and H with the funny letter is the reduced Planck's constant. So what they do to scale the energy proportional to make the physicality of the photon zero as the energy scales is this reduced Planck's constant um, basically scales all the energy proportionally to zero, so that it actually has no physicality, but it still has the ability to have momentum, right? So that's how they mathematically facilitate that. So, but the use of Planck's constant and all that, which we'll get into here in a second with hertz and frequencies and whatnot. So, all these are wave equations. The physicality of the photon that is required of it to propagate through a vacuum only exists in our imaginations. If the conceptual mathematic extrapolation of the physical is of the physicality and behavior of the photon existed as described by the wave equations, the length of the photon would be directly proportional to the length of its wavelength of the wavelength's existence. So the speed of light is set by c. So that's 2,900,792,458 meters per second. And this means that a photon that exists at a frequency of 3 hertz for 1 second would be 300 million meters long conceptually. So, like, if they were trying to attribute the physicality, to it, because a lot of people seem to think that there's an experiment that proves that there's a wave particle duality and that sort of stuff. So, similarly to how there's no instant action at a distance, but there's no time variable in Newton's equations to account for the propagation of gravity, for gravity. There in Planck's equations, there's no time variable either. So by default, it's set to 1 second because Planck's constant was derived. His solution was derived from a data set. That curve from the black body radiation is from a data set that's 1 second long. So everything defaults to that. So the so if you're a wave particle duality person, the physicality of the photon that you believe in would by default have to be proportional to the existence of the wavelength, right? So if it propagated for 1 second, it would be 300 million meters long because the speed of light is 300 million meters per second.
We got to
Let's
come back to
see.
that.
Absolutely, absolutely. So there we have that.
That's true.
All right. So, and then we're going to get into a little mathematical analysis of relativity theory. And a lot of this analysis was by Stephen Crothers. And I'm just going to break down some of the terminology here to familiarize us with the lingo here. So we have examples of tensors. So the Einstein tensor. So we got your GUV, your Ricci tensor, your RUV, your pseudo tensor, your TUV, and all that. So when we're talking about the different types of tensors and the equations, that's what they're represented by. So the words covariant, when you hear covariant, this is used to describe a tensor that under transformation is in accordance with the rules of covariant transformations, meaning that the geometric properties, when transferred to a new coordinate system, are independent of the new coordinate system, meaning that they don't change. So when the speed of light is transformed to another coordinate system, so it's represented by c, right? So that speed, when it's transformed to a new coordinate system, it has to be the same. So there's laws for conservation laws and stuff like that are represented mathematically. So the pseudo tensor here is for the conservation laws. So things like this have to produce invariant transformations to be covariant, and covariance is supposed to establish a meaningful relationship with the mathematics, with the abstract mathematics, and in reality, right? So if your theory is mathematically covariant, it's a good indication that you're not just making things up to cook the book, so to speak, right? So it's like that's how you would indicate that, because we've all kind of heard um, uh, about reference frames and how things are how the speeds of things are the same in all reference frames, and how this was validated by this reference frame and that reference frame. And it's like, who went to the reference frame to validate it? Well, they do it mathematically under transformations with these laws of physics. And when they transform them to the new reference frame, as long as the coordinate system has, contracted time and time is dilated proportionally, they can get their calculations out of it, and it gives the appearance of covariance. Now, the thing with the way that Einstein, with the way with the evolution of the mathematics for Einstein's theory, he ended on absolute differential calculus, where you could use these metric tensors and indices to describe coordinate systems within them and all that. Um, when he switched to that differential calculus, the thing with that is if you change the initial conditions or the boundary conditions, you can kind of facilitate whatever you need to get the result you need to. So the relevance of covariance in that regard, even though it was already spotty before with just sticking to the algebraic transformations, but towards the final evolution of the theory in its current form allows for like it's already built into it to have you can just swap out a different tensor to get the effects that you need. Basically, is what's going on there. And then so to get into the analyzation of the tensors themselves is how we're going to analyze the validity of the calculations that they're producing, right? Because they are calculating, right? But is it real? Is it meaningful? Well, we're going to learn some terminology here and figure out if it is or not. So invariant means that a quantity that remains unchanged under a given transformation. Example, see the speed of light. So like I was talking about earlier, if your mathematic theory is covariant, then when you transform the laws of physics, those transformations will be invariant. Okay. So a transformation is a mathematical operation that maps a set of objects to another set of objects while preserving a certain set of properties of the original system. So this is just transforming from one coordinate system to another coordinate system, and then your new coordinate system is going to have corrections built in from the old coordinate system. So your new XYZ variables will be, your X variable might be X minus, some other variable or number that that's relative to the new coordinate system that you're transforming into. So a tensor is a mathematical object that represents a linear relationship between sets of vectors, scalars, and other tensors. A pseudotensor is a tensor-like object that transforms like a tensor under transformations, but not others. So it allows um, for you to transform to certain coordinate systems and like give the illusion of covariance, right? It'll make it look like that this is a covariant transformation, but if you transform that law of physics or whatever you're doing to a different coordinate system, it's actually going to break and not be a covariant transformation. So this is so you can they bring in the pseudo tensor to transform or to allow for that covariant relationship, right? So like I was talking about earlier, how you can change the boundary conditions. So you just swap in the your conservation tensor here, your pseudo tensor, and then you can extrapolate the effects you need to relative to your initial input condition for your space-time curvature. That sounds like a lot, but it's gonna hopefully make sense, but who knows.
Are you going to be able to draw this for us?
Draw? What do you mean? Like show some like do the math out and show you?
Yeah, we gotta. Yeah, because you're awesome with the slides and stuff like this. So I think what would be great would to be like compile a fucking transforming object, like little diagrams and figures of the photon, like as you on all together, like on one whiteboard, like keep adding, and then kind of have a summary shot of all of it from beginning to end. You know what I mean? That'd be kind of cool.
Yeah, that would be a good way to visually represent it. And if you would like to see someone actually do the math and extract it out, because what we're going to go over here in a second is this process of contraction. There's a video on that Sky Scholar channel that I mentioned earlier by a guy named Stephen Crothers. I can link the video. He actually goes through the process of this analysis that I'm breaking down all the terminology of and shows this first order intrinsic differential problem. It's really interesting to
Here we
watch,
go.
but it's kind of dry.
Here we go again. It's just so many terms and
Yeah.
like logical attacks, and you know what I mean. And it's just good to go back and you know what I mean. Like each point of logical attack, you know what I mean. It's wait, was this one in agreement? Was this one in disagreement? You know what I'm saying? Like
Yeah,
you
no,
just have it all kind of summarized.
yeah, they built it's really confusing, and there's a lot of discrepancies and hiding and the appearance of mathematics where they use these like literal mathematical logic fallacies to build the appearance of being able to like give these calculations. But what we're going to find out here is that these are physically meaningless calculations relative to the mechanisms in which they're trying to attribute the phenomenon to, i.e., the bending and warping of space and time. Um,
Right.
so a first order intrinsic invariant differential. So this is a type of invariant tensor that is coordinate dependent and changes under transformation. It is it is composed solely of the components of a tensor and its first derivatives. It is not derived from the field equations themselves and cannot obtain a second order and cannot be obtained from second order field equations, which violates the mathematical structure of the theory based on the principles of covariance, and that the idea that the physical laws should be independent of the choice of the coordinate system. So in reference to into what that means basically is, so the first two postulates of special relativity are that all inertial reference frames are equally valid and that there's no preferred frame. So these are, so mathematically speaking,
And that's so we could throw that motherfucker out because we all know that's some bullshit.
yeah. So mathematically speaking, they can try and like you facilitate that the truthfulness of that mathematically, right? And then the second postulate is that the speed of light is the same for all observers and is independent of the source or of the motion of the source or observer. So with that being said, they have let's see. Um, with that being said, they have a mathematical framework in which they can interpret experimental results and all that stuff, right? So they need God, that kind of threw me off. Let's see. Cannot describe themselves. Framework which violates the theory, the principle. Okay, yeah. So to facilitate like things like the conservation laws and whatnot, right? Like your boy Paul Lavue that came through in 1913 to explain length contraction and time dilation through a rotating device through a pseudo tensor specially derived, the Landau Lifshitz Fitzgerald metric or something like that. I think it's called. So to derive something like that, what they did is they derived it from this GUV instead of being from the original field equations. And that violation, and like, so what they did is like they packed in a way uh to like make it mathematically look like, they have a way to give a covariant transformation to everything, but they just kind of made that mechanism where, like I was saying earlier, how you can just swap in a tensor and swap it out. So contraction is a mathematical operation that involves summing all the components of a tensor in a specific way to extract information about the state of the tensor it's describing. So to think about that for a second, so if you think about the Einstein tensor here, this GUV, if you think about that, like I gave you instructions to bake a vanilla cake, and I said, here's all the ingredients you need, and here's how you're going to make this 4-layer vanilla cake, and you're like, okay, cool, and you didn't have one of the ingredients, right? So you were like, okay, I'm just going to derive the ingredients from the ingredients that I do have instead of getting it from the list or whatever, like getting it from its own respective thing, right? You're just going to combine some stuff and you make your 4-layer vanilla cake and you present it to me and I look at it and I'm like, wow, it looks like a vanilla cake. You did it. And then I'm like, okay, well, let's verify that it's a vanilla cake though. So we verify that by compressing all 4 layers of that cake down into one layer. And when I compress that layer, it's not a vanilla cake anymore. It's actually a chocolate cake. And that's the, if that kind of gives an analogous way to describe what's going on with the transformations and the validity of the mathematics, where on the calculation it appears like they calculated something, but when you actually contract these tensors and do an analysis of the results that they derive, you find that due to the first order intrinsic invariant differential violation of the structure, it leads to physically meaningless results. Okay. And then, so conservation of energy and momentum. So these are the physical principles that state the total energy and momentum in a closed system are conserved over time. In relativity theory, gravitational fields in space-time curvature tends to infinity, which violates the conservation laws. So they had to have, that's why deriving this was so important, because if you weren't, if you couldn't describe the conservation laws, nobody was going to take relativity theory seriously. So they were forced to a position where they, sorry, for a second, they had to use this pseudo tensor to facilitate the appearance of mathematics. And when you really break it down and do a dimensional analysis of it through contraction, it's all a reification fallacy. And this was all pointed out by the two gentlemen that invented differential calculus. Forget their names. It's cited here on the next page, I think. I'll read it off when I get to it. But yeah, like this whole structure and everything, like this is all known about, and other people have pointed it out besides Crothers. But I like to point out his work because he actually has a video of him going over the mathematics and solving it, so you can see in real time what it looks like to contract it out and see the violation and the meaninglessness of it. And he doesn't define the terminology like I do here, so this will kind of give you some reference if you want to go check that out later, and then you can actually understand a little bit what he's talking about, because he just kind of assumes everyone already knows what these words mean when he does it. And no one knows what a fucking first order intrinsic invariant differential is, So let's be real. So a second order differential equation is a mathematical equation that involves a function, its derivatives and its second derivatives. Einstein's field equations are second order differential equations that describe the relationship between spacetime curvature and the distribution of matter and energy within it. The curvature of spacetime is affected by the presence of matter and energy within it, right? And so to just give you some reference on what those equations look like again, so there's your TUV. So they have the upper indice in this iteration of it, but they later use all sub ones. So, um, so yeah, this violation was pointed out by what is it? Sometime in the 1920s. I don't have the exact date, but it was pointed out by a Russian guy named Luganov and uh, Metsa, that guy. So anyway, those two gentlemen pointed out this as well from back then. So this is like a well-known thing that just isn't really talked about. Um, let's see. Oh yeah, so Ricky Cabastro and Levi Savita, those are the two gentlemen that invented differential calculus and basically the framework that Einstein used and all that. And then so the metric that so all the metrics for the conservation laws that are used to calculate these, to make these calculations and stuff are all first order intrinsic invariant differential, logical fallacies, basically, right? So like it's physically meaningless in the equations. Let's see. So to close on it, it's all so to end on that mathematical analysis recap. So the tensor calculus used to describe an I-beam and the stress relationship between 2 points in it and all that, like, very meaningful, because you have to use real numbers, you have to use real values, real amounts, the real weight of something, right? You can't just make something up or bend a coordinate system to contract it to what you need it to fit something that you need as your measuring stick, right? So I'll read here from the conclusion, and then we're pretty much done, boys, and I'll open the floor to further discussion. So, how math became reality. Conclusion. In conclusion, the historical and classical experimental evidence put forward as proof of the theory of relativity does not support it and the theory has entirely collapsed in on itself at free fall speeds, revealing it to be a mathematical prank played on us all. In my opinion, there was a deliberate effort to promote the theory of relativity and make it widely accepted. Someone or some group of individuals realized that they could use this framework of spacetime curvature interpretation to manipulate the concept of time in natural electromagnetic phenomenon. This was done by using the spacetime metaphors supported by abstract mathematics. The term spacetime or spacetime curvature is misleading and imaginary. There is no experimental proof of the theory of relativity theory. Let's see. Oops. There is no experimental proof that the theory of relativity is anything beyond a mathematical framework. Space-time poses no physical attributes and cannot distort or alter a path a path of mass or massless objects moving along any non-existent curvature. Some individuals think that relativity theory has been verified because its predictions have been validated on several occasions. However, other concepts like Lorentz's ether theory also produce comparable outcomes. This issue with relativity theory, or the issue with relativity theory, is that it employs mathematics to predict successfully, but the way that it describes time and space is illogical and even goes against established knowledge. The underlying problem arises from the switch from Lorentz's concept of absolute time and a variable speed of light to Einstein's relative time and a constant speed of light. The Sagnac effect demonstrates the speed of light can vary based on an observer's position, which can make time appear to pass differently. The major differences between the two systems is that Lorentz system implies the stars, planets, and galaxies and other celestial objects are closer to us and exist in a denser medium. In contrast, the relativity theory is essentially an inverse of the ether theory, and of a close and of a inverse of a ether theory of a closer and denser medium, which allows for a broader range of interpretation concerning the distances and sizes and the nature of the phenomenon in a vacuum. 1 second. Had to get some water. My throat was getting dry there. Okay, let's see. Let's see. So broader interpretation for the sizes and distances for for the objects that we see in the sky. The reason why mainstream science can state with a straight face that a photon has traveled 13.7 billion years to reach our eyes and has covered a distance of 80 sextillion 600 who knows, quadrillion billion million miles is due to the inversion of that constant speed of time, or that constant speed of light in relative time. Experiments should progress the validation of theories rather than theories influencing the experiments, so that data can selectively be used to confirm the theory. All right. So I got a MediaFire link for all the sources from that presentation, if anyone's interested in them. And I think that was it. Cool.
Nice.
That's it.
You chopped that down to 2 hours and 4 minutes, dude. Holy crap.
Not bad, dude. The speed run, bro. Speed run. Oh. So is there any questions or comments or anything? I'll unmute that guy.
Oh, look, Glober's left.
There you go. All good. Sorry about that. EEEERA. I just wanted to get through that last bit there. I was almost done and wanted to close out on some high momentum there.
Dude, I love that part about the gravitational waves being detected, and they're like, yeah, and they're like, yeah, we did it, it's real, we did it, and then like, actually, okay, so what happened was we made it up, but it was like for really good reasons, and it was to help you, and they were like, yeah, that's okay, guys, and then later, like 2 weeks later, they were like, yeah, so we did it for real this time. People were like, yeah, and then that was it. That was the whole gravitational wave detection process as it unfolded in real time.
Yep.
Fucking nonsense.
Yep, and every couple of years, they release a paper saying that they made another detection. And similarly, those detections are made under similar circumstances, where that first one was made where their system wasn't fully operational after maintenance, and their safeguard for preventing false positives was down.
It's kind of
so it's like that's openly part of the first successful confirmation detection, where it's like, what was that, bud? You said you detected it while it wasn't fully operational and while it had no false positive way to eliminate that. What are you talking about there, bud?
That's one of those things. You can look at the historicity of it and remove all the science and the math and the equations and the elevated concepts that maybe you don't understand, and just look at it and look at what happened and go, oh, Yeah, no.
And just
It's
go,
fucked.
and just go,
Yeah. It's
nah.
like, yeah, like
Yeah,
honestly.
like, nah, I don't have to agree to that. Nah.
Like, well, like when you figure out that like NASA was founded the year after they explored Antarctica, I went, what? Wait a second. Everyone, don't look out. Look up. Look. Well, look. We're going to the moon. You know.
Yep. Yeah. So did the audio improve after I switched to a lower bit rate?
Yeah. Well, it was the audio was fine. It was the cam kept buffering, like it was stuttering and freezing, and like we heard the audio in your normal Discord quality, but
Oh,
it
it's just the
wasn't.
cam itself.
Yeah.
Oh shoot.
Yeah.
Okay.
It's all right. It was
Dang, I
fine.
should have. That's okay. Yeah, I wanted to do the whole thing on cam, but that's all
Yeah.
good.
You turned it off immediately, and I was like, well, I guess that is better. But I meant like,
Well,
but you were
well, I
doing a
don't have my
virtual
OB.
cam, so yeah, I didn't know.
Yeah, yeah. The way I have my OBS set up, it wouldn't. Anyway, we can talk about that later. But yeah. Is there any questions, comments, concerns? Any like anyone ever have a relativity question? You were like, oh, I wonder what happens if or what the explanation is. You know, hit me up.
Atomic clocks, cesium atoms, all the crazy oscillations. How about the fact that it's the most provable, repeatable Michelson-Morley non-ether null experiment that they can keep repeating, except that they got to keep changing the parameters in the arms and put it in the basement and to get different results and like do it a little bit crooked. I mean, no, does anyone want to bring that up?
Yeah. Yeah, that's one of my favorite ones because like Einstein was saying, Dayton Miller just absolutely obliterated the theory with his measurements, and then his work was actually has been reproduced since then by two different people. And then the effect obviously showing to persist without rotational effects. So like they eliminated their one mechanism for even explaining it through the way that they had to mathematically co-opt it through a mathematical reification fallacy to inform their coordinate system,
Oh,
proportionally.
hold on, I have a
They,
tensor for that. Don't worry about it, bud.
yeah, hold on, there's a tensor for that, bud. Yeah, yeah, man, awesome, dude.
Excellent work, dude. Thanks again for bringing this awesome work to the forefront so that we can be properly armed with the knowledge that our forefathers already possessed.
Yeah, man. The motivation for this presentation was I would watch Witsit debate people on relativity theory, and he would just like, just dunk on it, obviously. And then they would be like, nah, it was proven. And then they would just like cite Wikipedia and be like,
Right?
Pound Repka explains this. I was like, okay, well, let's see. And then I read the paper and it was like, well, turns out we don't really support relativity theory and we actually can't make any positive claims on it. Maybe somebody will figure it out at a later date. And I was like, oh, really? So I was like, okay, well, let's just go through all of the big ones. So yeah, this whole list that I went through was basically if you go to Wikipedia and type proof of relativity theory, you'll get everything on this presentation pretty much
Nice.
to the T.
Which is so astounding.
So yeah, you have well-equipped information on how to describe everything and all the relativistic effects and all that.
And once you have the totality of the knowledge, you got to be like, how fucking dare they? They took everything that refuted their model and like proposed our model, perpetuated ether theory, an energetic background, confirmed stationary, non-moving in every reference frame, confirmed preferred direction only inherent to a flare. And they were like, that's all globe proof. And people were like, fucking flirts, look, it's globe proof. Well, like, and we were like, oh yeah. Nobody looked into it, dude. What the hell?
Yeah. They just browbeat everyone and told them that they weren't smart enough to understand it.
And we bought it and we let them do it.
Yeah. And then we thought we were cool, talking about black holes. Like I can't tell you how much I used to love black holes, boys. That was my favorite like space-time event. Like I couldn't learn enough about them, Just loved it.
Right?
It was so cool.
Dude, mathematical boogeymen based on sky demons. That's awesome.
Yeah, based on a sky demon predicted by a sky prophet. Yeah, it eats light. Yeah.
Stuff of bedtime stories, man. Well, Jackie.
Yeah, so we can go ahead and wrap up the presentation if there's no further questions, comments. I'll go ahead and stop streaming. And then Shane, if you want to roll an outro or end it however you want to end it, let me know and I'll close it out.
Yeah, we can do that.
I'll stick around for a little bit if anyone has like delayed questions or whatever, but I'll be right.
Well, you don't know if it's part of the show. Welcome to the show. If you don't know, it's part of the show. Didn't they teach you to reach for the stars while opening up the bars and keeping you chained down with mortgage bills and cars? Vaccines for your arms, kids sounding like supercharged, caffeinated hate-filled scars and rage-quit repertoires. No answers for yards, caught up in emotion that's not even yours. Imposter truths like impeccable retards, lined up for your serving of gish galloping wars. No remedy can save the lost, in love with the yarn. I'm tired of walking into refracted shards, poor science displayed by disgusting bards. Soaked in sin with your dupe is delight and a new hand of cards. Been so long, seems like for love I'm just too hard, I said. Welcome to